starting point for today's lecture is the observation that we made last time, that time evolution can be regarded as a time-dependent canonical transformation. And we are wondering which generating function generates that time-dependent canonical transformation. I told you last week that it will turn out to be the action, and that's precisely what I would like to prove here first, that this is indeed the case. As a starting point, let's have another look at the action, and you may recognize the title. You see in the title that it doesn't say action functional, but it says action function. So it's a subtlety, but it's a hint at what we are going to do. Remember how the action was defined in configuration space. We are back to configuration space. We have a time axis here, and we have just the configuration Q. As usual, I just draw that in one dimension. And remember, when we looked at the action, what we did, we fixed the initial configuration. At some time t0, we had some configuration q0. That's the initial configuration. And then at some later time t, we have a configuration q. And in between, there is a trajectory. Now, for the purposes of the discussion here, I would like to consider not arbitrary trajectories, as we did when we looked at the extremization principle for the action, but I want to look at the actual physical trajectory. So the trajectory that I drew here is really the physical, and hence the extremal trajectory in configuration space. Now the initial time t0, this one we keep always fixed. The initial configuration q0, I want to give that the letter capital Q. Just a little remark, there's a slight change in notation here with respect to last week. Last week when I argued that time evolution can be viewed as a canonical transformation, I denoted the initial coordinates with small letters and the final coordinates with capital letters. Here it's the other way around. I apologize for that, but it's just a little break in the notes that I brought along. Here it's the other way around. We will use the capital letter Q for the initial configuration, and we use the small letter q for the final configuration. And now, as I said, we focus on the physical trajectory. It's specified by initial time, initial configuration, and final time, final configuration. The initial time t0 we keep always fixed, but the other three parameters we allow to vary. So we allow both little q, capital Q, and t to vary. And then we look at the action for the physical trajectory. And now, since the trajectory is given, it's the physical trajectory, there's no freedom in the trajectory, It's no longer a functional, but it's a function of the three parameters little q, capital Q, and t. Yeah? So what we do is we take the physical trajectory let me call that gamma. We consider the action, which is defined, of course, as the integral of the Lagrangian along the trajectory gamma as a function of little q, capital Q, and t. Let me next go from configuration space to extended phase space. Again, we limit ourselves to one dimension. So we can draw it. And here we have, on the one side, we have the ordinary phase space with coordinates p and q. And we have the additional dimension time. Now let's say that here on the left we start with time t0. We have as our initial configuration, we fix our capital Q. So the initial states are constrained to lie on the vertical line at time t0 and configuration capital Q, but unspecified momentum. So let me indicate here this vertical line. This represents the initial condition. And let us, for the purposes of this discussion, say that the initial configuration is fixed. And it's fixed at this capital Q. Let's pick a state on this vertical line, state satisfying this initial condition. Once we've picked a point in phase space as our starting point, as our initial state, there's a unique physical trajectory. Let the physical trajectory be this trajectory gamma 1, this curve gamma 1. This curve ends here at this point, and this point corresponds to time t and configuration little q. What would have happened if we had chosen a slightly different initial condition? Still on this vertical line, so still at given initial configuration, but with a slightly different initial momentum. So let's pick alternatively a point here. Now this initial state would evolve on a slightly different physical trajectory and end, say, at that point. That's curve gamma 2. That point need not necessarily be at the same time t. It can be sort of the evolution might end at a slightly different time t plus some dt, and it will end up in a different configuration. So let me try to indicate that. We have another vertical line here. The end point of the second curve corresponds to a time t plus dt, and it corresponds to a slightly different configuration slightly different configuration, q plus dq. Okay, so again, these are the green curves. It's important to note that these are physical trajectories. And now, rather than in configuration space, they are in extended phase space. So again, just let me note that these are physical trajectories now in extended phase space. Now, associated with each of these two physical trajectories is an action. So for both trajectories, we can evaluate the action. So for the trajectory gamma I, where I is 1 or 2, we have the action SI, which is the integral along the respective trajectory, gamma I, and then the Lagrange function times dt, L dt, or dt prime. The Lagrange function is related to the Hamilton function by Lagrange function is equal to momentum times velocity minus the Hamilton function. But now we can also write it in a slightly different way. The first of these terms, q dot, that's dq over dt times dt, gives dq. So we can also write that as the integral of p dq minus h dt. Now perhaps this is something you recognize. Last week when we had considered these tubes, we had introduced the vector field of tangent vectors along the physical trajectories. Let me show that to you, what we did last week. Here we had looked at the physical trajectories, and we tangent to the physical trajectories are vectors W. These form a vector field. We had determined last week the components of that vector field. We had verified that the divergence of that vector field vanishes, and that therefore, in one dimension at least, this vector field can be written as the curl of a different vector field. And that vector field, that new vector field x, had the components p, 0, and minus h, minus the Hamilton function. Keep that in mind, and now look at the integral that we have down here. We have p dq minus Hamilton function times dt. That is the same as the scalar product of an infinitesimal distance vector in extended phase space, scalar product with that vector field x that I just showed you. Because this infinitesimal distance vector here in extended phase space, that has the components dq, dp, dt, and that vector field x, remember, had the components p, 0, and minus the Hamilton function. When you take the scalar product of these two, then you get the same expression as the previous integral. So this is the first observation that we make, that we can write the action in terms of this vector field x that we had introduced last week. When we look at these two trajectories, they are very close to each other, and we can create a closed loop if we connect the endpoints of these two curves. We can introduce here an infinitesimal curve going in this direction, which I call alpha, and another infinitesimal piece, which I call beta. And then together, these four pieces, gamma 1, gamma 2, alpha, and beta, they form a closed loop in extended phase space. And that's going to be useful in the following calculation. I would like to look at the difference in action between the two trajectories. So I'd like to look at S2, the action associated with trajectory number 2, minus S1, the trajectory number 1. So we look next at the differential, the difference between the two actions. And the two trajectories both had the same initial condition for the configuration. So we are looking at the action differential at fixed initial configuration capital Q. The differential ds, so that is defined as the difference S2 minus S1. We just had seen that the action can be regarded as this line integral of the vector field x. So we can write this is the line integral along trajectory number 2 minus the line integral along trajectory number 1 of the vector field x. Okay? I left these spaces on purpose because we can work a bit with this expression and add and subtract terms without changing the end result. One thing we can do is we can subtract from this the line integral along this infinitesimal piece beta that I had introduced, and then re-adding it later on. So plus integral along beta, line integral of this vector field x. So this doesn't change anything. Something else we can do is that we can add here the line integral along the other infinitesimal piece alpha. And this we don't have to compensate because that piece doesn't contribute. This line integral is equal to 0. That is because when you look at the in the integrand, you have the scalar product of this infinitesimal line element dxi with the vector field x. Now along this curve alpha, look at this picture. When we go along this infinitesimal section alpha, all we vary is the second component in extended phase space, because the q coordinate is constant and time is also constant along alpha. Only the p component changes. So the infinitesimal line element has components 0, dp 0. The vector field x, on the other hand, has components p 0 minus Hamilton function. You see that this scalar product vanishes. So in other words, it doesn't hurt to introduce this infinitesimal section alpha. What I just enclosed inside this box, this is actually a full loop. If you look at the 4 contributions to the line integral, so along gamma 2, then beta, then gamma 1, then alpha, and you consider the signs in front of these integrals, and you also consider here the arrows, so how the direction that I introduced for these trajectories. So when you take into account the direction of these trajectories and the signs in front of the integrals, then these 4 contributions add up to a closed loop. So this is in fact inside the box. This is in fact a loop integral of this vector field. And I have yet to specify whether I mean the clockwise or counterclockwise loop. I mean here the counterclockwise loop, and therefore I have to give it a minus sign. Now, once again, we've done that several times in both directions. We can apply Stokes' theorem. This is a line integral around the closed loop. This is the same as the area integral of the curl of that vector field. So this is nothing but the area integral of the curl of x, where I should indicate in this drawing where the area is and where this vector, this infinitesimal area vector df is. So we're talking about this area here, this shaded area, which is encircled by the closed loop. And you have an infinitesimal area element df. If we look at the loop counterclockwise, then the infinitesimal area element is pointing upwards. So this is an infinitesimal piece of that. All right, so we have this. We have transformed it into an area integral, and now we use yet again the fact that the curl of this vector field x minus the curl of x gives the tangent vector w along of the physical trajectory. So this equals then the area integral of w, where w is the tangent vector to the physical trajectory. Here too, I would like to indicate the w in our figure. So I go back one more time, and I would like to indicate here, say at this point, that there's the tangent vector w, and here as well there's a tangent vector w. Now you see from this picture the fact that the w's are tangent to the physical trajectories also means that they are tangent to this shaded area. So this the scalar product and the infinitesimal sort of directed area element df, that's perpendicular to the area. So the scalar product of W with df vanishes. They are perpendicular to each other. So in other words, this area integral here is equal to 0 because W is tangent to that area. Now this is a very helpful result because then only the single term outside the box remains. Yeah? So we have the result that the action differential is simply the integral along beta, this infinitesimal piece beta, infinitesimal line integral of the vector field x. Again, let's have a look at the components of this infinitesimal line element. So the infinitesimal line element has the components dq, dp, and dt. The vector field x has the components, as before, momentum, 0, and minus the Hamilton function. So, in other words, we can write this, and now since the section beta, that's just an infinitesimal piece. So, actually, this is equal simply to p dq minus Hamilton function dt. So there's no actual integration taking place here because beta is just an infinitesimal piece. So this is the first result about the differential of the action. It's given by p dq minus h dt, where the dq and the dt relate to this, refer to this infinitesimal section beta, which is the sort of the distance vector in extended phase space connecting the two possible endpoints, the two endpoints of the two trajectories. So the dq and the dt relate to the final state, the final state in extended phase space. So these are the coordinate differentials of the final states. And this holds at, just remember what we said at the beginning, that this is at fixed initial condition. So that is at fixed Q. This relationship here tells us already an interesting result. Because if we view the action as a function of the initial and the final configuration and the final time, so a function of little q, capital Q, and little t, then this relationship here for the differentials tells us that little p must be the partial derivative of this action function with respect to little q at fixed capital Q and fixed t. Yeah? And the second part, the minus h dt, tells us that h, the Hamilton function, is minus the partial of s with respect to t at fixed little q and capital Q. The first of these two equations perhaps reminds you already of a generating function, because remember we had introduced the generating function as a function of the old and the new configurations, and time, if it's a time-dependent canonical transformation. So we had old coordinates, little q's, and new coordinates, capital Q's. And we had found the relationship for a generating function that the momentum in the old coordinates, so the little p, was given by the partial derivative of the generating function with respect to little q at fixed new coordinate, capital Q. So exactly the same relationship as the first of these two relationships here. You have to distinguish carefully between sort of initial state and final state in the sense of a time evolution, and old coordinates and new coordinates in the sense of a coordinate transformation. In the formalism of the generating function, we have the generating function as a function of old coordinates and new coordinates. And here we have the action as a function of initial coordinates and final coordinates. And that's perhaps a bit unintuitive, but what one does here is that one identifies the final coordinates, the coordinates of the final state, with the old coordinates, and the coordinates of the initial state with the new coordinates. So the initial that's why the initial condition gets the capital letters. So you have the identification initial state or final state equals old, and initial state equals new coordinates. That's perhaps the source of the of your question, which is of course a very valid question, because intuitively one would say, well, initially I have old and then finally I have new, but here it's just the other way around. Yeah? Because the when you talk about old coordinates or original coordinates and new coordinates or transformed coordinates, this doesn't say anything about the time order of the two. It's just that's just a convention. You just pick one to be the original coordinates and the other to be the transformed coordinates. We can now make a very similar consideration as before, with the difference that rather than keeping the initial configuration, capital Q, fixed and allowing variations of the final configuration, we do the reverse. We now keep the final configuration fixed. So we require that these neighboring trajectories, they both end up in the same final configuration, little q, but they possibly have, and they generally will have, slightly different initial configurations, capital Q. So here we keep the final configuration Q fixed, and we allow variation of the initial configuration, capital Q. And then we can apply the same logic, we can do the same construction and basically repeat the same argument. And we will also find a formula for the differential of the action. And from that formula we will infer that the initial momentum, capital P, is again a partial derivative of the action function. It's the partial derivative of the action function which is a function, we said, of final initial configurations and time t, with respect to the initial configuration, capital Q, at fixed final configuration, little q and t, with a minus sign. And this here is the capital P is the initial momentum. We can summarize the results from the previous page and this result here, which you can obtain in an analogous way. We can summarize that in the following form. We can write the differential of the action. We can now allow variations both of the initial and the final configuration, and then the general expression has the form, it's little p d little q, so this corresponds to variations of the final configuration minus capital P d capital Q, which corresponds to variations of the initial configuration, and with minus the Hamilton function dt. What we did not vary, not even in the second case, what we did not vary was the initial time. So the t0, that is always fixed. Yeah? So I note that we keep the t0 always fixed. So this is the final result for the action differential. Now we are ready to prove the claim that time evolution is generated by the action. So we have the action function as a function of initial and final configuration and also of time, sort of the final time t. And as such, of course, we can view it as the generating function of a canonical transformation. What we have to check is that the canonical transformation that it generates is actually the one corresponding to time evolution. So what we do, as I said, we consider the action function S, which is a function of initial and final configurations. We can consider that as a time-dependent generating function. We know that we showed that the partial derivative of this action function with respect to little q, which is the final configuration, gives little p, which is the final momentum, and we also showed that the partial with respect to capital Q, which is the initial configuration, gives minus the initial momentum. This, as we had seen quite generally for generating functions, these two equations give us the possibility to define a transformation law between old and new coordinates, between small letter coordinates and capital letter coordinates. So this defines a time-dependent canonical transformation going from the old coordinates, which for us are the small letters q and p, to the new coordinates, which are the capital letters. And as we said before, and also in reply to your question, what we call the old coordinates are the coordinates of our system at the final time t. So these are the coordinates of the final state at time t, and what we call the new coordinates in the sense of coordinate transformation are the coordinates of the initial state. So the coordinate transformation in phase space is actually going backwards in time. We are mapping the coordinates of the final state to the coordinates of the initial state. So in a way we are undoing, we are reversing the time evolution. We are going back to the initial state. What do we expect from that? We expect that in the transformed coordinates, there should be no dynamics at all. There should be the dynamics should be trivial. Because, precisely because the canonical transformation is undoing, is reversing the time evolution. So when the system evolves in time, the coordinates of my system in phase space change, but then I apply a time-dependent canonical transformation which exactly reverses that change. It maps me back to my initial coordinates. Then I'm stuck at my initial coordinates, and there's no change at all. So that's what we expect, that the dynamics in the transformed coordinates is trivial, precisely because the transformation reverses or undoes the time evolution. And this is indeed the case. Because what we can do is we know how the Hamiltonian transforms under a time-dependent coordinate transformation, canonical transformation. We saw yesterday or last week, we saw that the transformed Hamiltonian after a time-dependent canonical transformation is the original Hamiltonian plus the partial derivative of the generating function with respect to time. In our case, the generating function is the action function. But the partial derivative of the action function with respect to time, keeping small and capital q's fixed, we saw that that was minus the Hamilton function. So this is Hamilton function minus Hamilton function, which is equal to 0, and that's precisely what we expect. After canonical transformation generated by the action function, we have eliminated all the dynamics. And that's another way of seeing that indeed the action generates time evolution. If you want to be precise, it generates the reverse time evolution. It undoes the evolution. It takes you back to the initial state. So, strictly speaking, the canonical transformation that corresponds to time evolution is the inverse of the time evolution, or of the canonical transformation that is generated by the action function. Now, this paves the way for the Hamilton-Jacobi equation. So now we are in the middle of Hamilton-Jacobi theory, And the basic idea is the following. And this actually there are mechanical systems whose equation of motion can only be solved with Hamilton-Jacobi theory. So they're not the common examples. They are more sort of more complex examples than the ones that we've seen so far. But there are actually cases where Hamilton-Jacobi theory is the only approach that has worked so far to solve equations of motion. The basic idea is the following. Now that we know that time evolution corresponds to a canonical transformation, and that canonical transformation is generated by the action function, not the. Remember, we're here not talking about action as a functionale, but we're talking about a function. That is the starting point for the basic idea of Hamilton-Jacobi theory. If you want to find the time evolution of a system, that you start with the action. You try to find the action function. And once you have the action function, then you can derive from that the canonical transformation, and from that you get the time evolution. So the basic idea is try to find the action function. And once you have that, you get from that a canonical transformation, and from that you get, strictly speaking, the reverse of time evolution. So that is the central idea of Hamilton-Jacobi theory. Now we know one of the equations that we showed was that the final momentum, little p, that was the partial of the action function with respect to final configuration, position, at fixed initial position and time. And we also know this relation here for the Hamilton function. It's the partial with respect to time. Now, this implies, obviously, that Hamilton function plus the partial of s of the action function with respect to time, that this must be equal to 0. The Hamilton function, in turn, is a function on phase space. Possibly it's explicitly time dependent as well. So it's a function of q, momentum, and time. But momentum, we know that's the first of the above equations. Momentum we can replace by the partial of s with respect to q, and then time. So we use this relation in here, and we use that relation there. And this is called the Hamilton-Jacobi equation. And that is a partial differential equation for the action function. So we can say we consider the initial configuration capital Q to be fixed. That's an initial condition, and then S is just a function of the final configuration and time. So a function of these two variables. And then for the action function, we have this partial differential equation, which is the Hamilton-Jacobi equation. Strictly speaking, it's the time-dependent Hamilton-Jacobi equation. And the basic idea how you can use the Hamilton-Jacobi equation to solve actual problems in classical mechanics is the following, is that in a first step you solve the Hamilton-Jacobi equation to obtain the action function as a function of final position, initial position, which you consider it's an initial condition, it's a fixed parameter, and time. Then, in a second step, you use the relation for the momentum as a partial derivative. So these relations here, both for the final and the initial momentum. And once you have that, you can solve for the new coordinates in phase space, Q and P, as a function of the initial state and time. And that is the solution of your equation of motion. So these two basic steps. Once you have solve the Hamilton-Jacobi equation, you have the action function. Then by taking the partials, you get the momenta, and then you solve that for the final phase space coordinates as a function of the initial phase space coordinates and time, and that's the solution for the equation of motion.